In the last module, we talked about complexity of different problems in terms of big O, big omega, and big theta notation. Today, in this module, I'm going to talk about complexity of decision problems and different classifications for the same. First of all, what is a decision problem? Decision problem is a problem where the answer is yes or no. The answer is not compute something, the answer is say yes or no. So it would be things like I'm given a formula and I would like to know is it satisfiable. I'm given a graph, I want to know whether it is connected, etc. One kind of problems that we talk about in this case is called a tractable problem. That means there exists a polynomial time algorithm. That means its complexity is big O of some polynomial in the size of the input that can be used to solve the problem. These problems are class P, that is problems that can be solved in polynomial time. You could argue that once we get into problems like n to the power 10, whether they are really tractable, but generally these problems that we come across are n square, n cube type of problems, and these are something we can solve fairly easily. Intractable problems are problems where we do not know of any algorithm that solves the problem in polynomial time. It doesn't necessarily mean that there does not exist one, it's just that we don't know of one as of yet. That said, most of these problems are believed to be not in P, that is, we believe that they don't have a solution in polynomial time, it's just that we have not been able to prove that so far. Unsolvable problem is a problem for which there is no solution. I want to sort of distinguish between intractable and unsolvable problem. Intractable means it's difficult problem, but given in sufficient time and space, we can solve it. It's just that to solve it in a reasonable time does not seem to be feasible. Unsolvable means that there is no solution, there is no possibility of finding a solution because we can prove that a solution does not exist. We can generally show this by proof of contradiction. That is, if a solution exists, then something else will break, and that's something we are not allowed to do. This is one of those instances where I'm going to go in what I call preaching mode, and I want to sort of tell you what about the difference between mathematics and other sciences, say physics, chemistry, biology, etc. This is a question that I have been asked by my children, as in, they hear this thing that, oh, there was this Newton's theory of gravity and about stuff, and then Einstein came about and showed that some of that was wrong and he replaced it by something else. Now the question is, could the same thing, so essentially what this means is you could say that Einstein broke physics and maybe fixed it with something else, but he broke it first. The question is, can something similar happen in mathematics? And the answer to that is, I'm going to argue that mathematics is different than other sciences in this sense. What mathematics is trying to do, or what proofs in general we are trying to do here, is we are going to try to show what can be derived based on known hypothesis. We never want to be in a situation where we can prove something that turns out to be false, because then what we prove has no meaning. By contrast, if you think about physical sciences, let's say physics for example, then what we are trying to do there is we are trying to capture what reality is in some representation. So if some of those representations turn out to be false, then yes, it's a big problem, but it's not a disaster. It's not a disaster because it generally means we replace it by a better, different theory. In mathematics, we can't do that because what we are saying is what is it that we can prove? And if we prove something that turns out to be false, then maybe everything else that we have proven may be false as well. And in this sense, it is different. And so, for example, when we say the halting problem, now the halting problem is you're given a program, an arbitrary program, C++, Python program, whatever you like, and the goal is to decide whether that problem is going to terminate. This is a problem that is unsolvable. That means there is no solution that can exist for such a program, so for such a problem. By contrast, intractable problems are problems where we don't have a solution. Maybe we even believe that such a solution does not exist, but if somebody finds a solution tomorrow, it would be just fine. This is something we can deal with fairly easily. On the other hand, a solution for halting problem will not exist. It's not because that it doesn't exist because we haven't been smart enough. It's that it cannot exist because if it did, then it's going to lead to a contradiction in mathematics. That's something that we don't want to have. The next class that I want to introduce is the class NP. It stands for non-deterministic polynomial. It means that these are problems that can be verified in polynomial time. We may not be able to find a solution in polynomial time, but if I give you a solution, I can check whether the solution is right in polynomial time. NP complete is a class of problems where if you could find a polynomial time solution to any one of those problems, then it can be used to solve a polynomial time solution for all problems in NP. What this means is NP complete is the class of problems where these are the hardest problems in some sense in the class NP. The P versus NP challenge or P versus NP problem is one of the most famous problems in computer science that are currently open. The question asks, is the class P is equal to NP? Are there problems whose solutions can be checked in polynomial time, but they cannot be solved in polynomial time? Note that just because no one has found an algorithm so far, it doesn't mean one does not exist. It's just maybe that all of us collectively have been too stupid to find one, but maybe there exists one. And that's the question that we want to answer in P versus NP problem. That is, if I have a problem that I can verify a solution in polynomial time, does that guarantee that I would be able to solve it in polynomial time as well? Currently, there are problems where we can solve them, we can verify them in polynomial time, but we cannot solve them, as in find a solution in polynomial time. If a polynomial time algorithm for any of the problems in NP complete class are found, then we can use those to solve any other problem in the class NP. And this is why NP complete problems are important, because they tell you that okay, if you could solve this, then you could not only find a solution to that one problem, but you would be able to find solutions, polynomial time solutions to all these other problems. So one of the problems in this is satisfiability, and this is something that is discussed in the book in the first chapter. Most people believe that P is not equal to NP, but so far we have not been able to prove this, because we have not been able to show that there is some problem for which a polynomial time solution does not exist. There is a lot of money at stake here, so if this is something that interests you, proceed, but proceed with caution. It is open for last 50 or so years for a reason. I'm going to introduce a few problems that appear to be simple but are often difficult. I'm going to sort of relate to where these problems come from and give an intuition as to why they appear to be difficult, or they appear to be simple but are actually difficult. So here is a problem. Given a Boolean formula, a well-formed formula, the question is it satisfiable? In other words, is there a way I can assign it values to make it true? This is important for program verification. So let's look at why we have this problem as important. So let's look at some code. This is some random code that I wrote, not following any programming language per se, just some pseudocode. So let's imagine that I have some code over here that creates a variable and makes sure that the value of x is less than or equal to 10. Less than 10. Subsequently, we have some code. It sets x is equal to y plus 3, y is equal to z plus 3, x is equal to x minus 3. And we would like to know at the end, can the value of x be more than 10 at this point? Now we can create a formula to help us answer this question. So let's see how we can do that. So here I have x is less than 10. So I can write a formula that says x is less than 10. Now let's see what this statement does. The next statement, x is equal to y plus 3. What does it do? It changes x to y plus 3 and leaves everything else unchanged. So here I'm going to say x prime, which is the new value of x, is equal to y plus 3. Remember, y is the old value of x at this point. Y prime is the new value of y. It will be same as y because we didn't change y at all. Z prime is same as z. So I introduced three new variables, x prime, y prime, z prime, and I added some constraints based on that. So I'm going to have the first constraint and the second constraint satisfied. Then I have the third variable, third line, y is equal to z plus 3. So this will require me to introduce one more variable, y double prime. Now what is y double prime? It's going to be set to z prime plus 3. Z double prime and x double prime will remain unchanged. Now we can continue this. We can write a formula for the next line, and we can add a formula that says the last constraint, which is this one, and we would like to know whether the value of x at any point is greater than 10, and we will get a formula like this. Now let's see what this formula has. This formula is capturing the questions from this program. If the value of x could be set to more than 10 at any point, this formula would be satisfiable. That is, we could assign it values so that the formula evaluates to true. We can assign x prime, y prime, x double prime, y double prime, etc. a value so that this formula evaluates to true. If it's not possible for x to be ever more than 10, then that would mean that this formula is not satisfiable. It will always be false. So this is why we care about the satisfiability problem, and this is one of the reasons why we care about satisfiability problem. But it turns out that this problem is challenging. The most straightforward way to solve the satisfiability problem would be to write a truth table. Unfortunately, the size of the truth table is exponential in the number of variables, and so that's why we cannot use that. It's not a polynomial time algorithm, but we can do things that are more efficient. We just can't prove that they will work all the time, and this is one of the reasons why this problem is challenging. This is one of the problems that is in fact NP complete. Okay, this is another question that appears to be simple but is challenging. So let's look at this question. Is there x, y, z and n such that x cube plus y cube plus z cube is equal to n? Now we are going to specialize this problem by giving you a value of n. So we are going to specify the value of n, and then we are going to ask you the question, is there x, y and z such that x cube plus y cube plus z cube is 20, 25, 30, etc. Note that x, y and z could have to be integers. They could be 0, but they could also be negative. What if n is 29? Pause here for a little bit. I am going to ask you to think about what possible values of x, y and z you could have if n is equal to 29. What if n is equal to 30? Again, I'm going to ask you to pause, think about whether you could find a solution. Now, for n is equal to 29, I assume you came up with a solution by yourself. I haven't written it on the slide, but you should be able to come up with a solution for n is equal to 29. It's fairly straightforward. But for n is equal to 30, there is a solution. It's just that the solution is kind of difficult to get by just thinking about numbers. What if n is equal to 33? Turns out that this is actually an open problem. We don't know whether a solution exists, and we don't know that it does not exist either. This is another problem that is challenging. You are given a number n that has exactly 2 prime factors. So it would be something like 35, 21, etc. And your job is to find those 2 prime factors. Now, let's imagine that we use this algorithm. This is a fairly simple algorithm. For j is equal to 2, j less than n, j plus plus. If n mod j is 0, then print j and n comma j, because those are the 2 factors, and exit. Otherwise, keep going. This algorithm appears to be polynomial. This is appears to be polynomial because it looks like I'm running this in big O of n, but it's not polynomial because we always compute the complexity of the algorithm in terms of the size of the input. And what is the size of the input here? What is the input? The input is number n, and to represent number n we just need log of n bits, and that means the algorithm is actually exponential in the size of the input. We believe strongly that prime factorization is difficult, and it is something that is not feasible to do in polynomial time. It's not something we have proved per se, but uh, we have done sufficient work in this area where it is unlikely that such an algorithm exists. The well known security protocol RSA is based on this observation, and we will study this algorithm slightly later in this class. A simple view of complexity classes you could have in terms of whether P is equal to NP or P is not equal to NP. In this case, we will have a class of problems. If P is equal to NP, then NP would be NP complete. On the other hand, if P is not equal to NP, we would have a structure that looks kind of like this, where P is a strict subset of NP. NP complete is a strict subset of NP, and there are other problems in NP which are not in P but are not an NP complete either. Once again, we have reached the check before you go ahead slide. This module was fairly high level, so this module will give you a lot of concepts that will be useful later in your computer science curriculum. Terms like interactability, NP completeness, etc., those would be important when you try to analyze different algorithms. Uh, these topics are somewhat challenging, but they are quite interesting as well in terms of uh, different problems and their complexity, how it varies, etc. So if you are interested in any theory related computer science, that would be something quite useful for you. One thing I want you to do first for this module is review the algorithm that we had for finding factors and see how long the running time would be if, let's say, n is a 64-bit number. Uh, you can assume that one iteration of the loop is fairly fast, let's say 1 nanosecond. How long will it take for you to find the factors? And let's assume that the factor itself uh, is say a 32-bit number, two 32-bit numbers multiplied into a 64-bit number. Now you can do the same analysis. What would happen if the number was 128-bit or 256-bit, etc. We have reached the end of the module, so please go ahead and do the review quiz for this module.